Hello, everyone. My name is Behrad Toghi. I'm presenting our paper in IEEE CAVS titled A Maneuver-Based Urban Driving Dataset and Model for Cooperative Vehicle Applications. This is a collaboration between me and my collaborators from Connected and Automated Vehicle Research Lab at UCF. And the work has been done under the supervision of Dr. Yaser P. Fallah. If you're interested in more details about this work, please feel free to reach on over my email or my personal website. I would be happy to give you more details about this work. So basically, let's start with what is our motivation and how did we think about doing this work. My supervisor, Dr. Yaser Fallah, had a previous work on model-based communication, which is basically an idea of transmitting more efficient data between vehicles. So as most of you probably know, connected vehicles use standards such as CAM or BSM to broadcast and share their information, such as position, kinematics, and so on. And what's happening right now is vehicles just share raw data. And that's what the current implementations do. However, we came up with the idea that instead of transmitting the raw data, we can transmit models and model parameters in order to take the advantage of the bandwidth more efficiently, and especially you know how important the bandwidth is these days. So we have a couple publications on this topic, on the topic of model-based communication. Again, if you're interested, please reach out. I'd be happy to share them with you. But during this project, we were facing this question that how can we classify and parse some pieces of the driving history that are meaningful. For example, one thing that you can think of is some maneuvers such as right turn, a U-turn, or a brake, or some maneuvers like these. These are meaningful pieces of information that we can use them to basically to work in the model-based regime. So then when we looked at the literature, we realized, okay, so there are a couple data sets, driving data sets such as ngSim and other large-scale data sets, but none of them are labeled based on maneuver. They are just data sets that are recorded. Basically, they put some login devices on some cars, and they just ask them to do their normal driving behavior. And those are not really labeled, at least in real time. So we realized we need a labeled data set in order to be able to extract these meaningful pieces of information from driving data. So what we did is we did more than 1,000 minutes of urban driving near the UCF campus in Orlando, Florida. Here you see a screenshot of the area we did our driving with some of our paths. It's actually more than this, but I'm just trying to get a screenshot. And the procedure was in this way, that we used a Ford vehicle, and because we were given by Ford Motor Company a logging device that we could use to access most of the CAN bus information on the Ford vehicles. And this vehicle obviously had a driver and an operator, which used a logging system that we designed and implemented to label these maneuvers in real time. Basically, whenever the driver made a right turn or a U-turn, the operator or the co-pilot made a label in real time on writing more information and labeling the data there. So basically, in this way, we had a very accurate labeling, because what most of people do is they collect their data sets and then they label them offline. Basically, they look at the data, which is mostly CAN bus data, as we will see sometimes is tricky, and then they just use it to basically label based on what they can see. However, here, because we are the co-pilot and the operator is in real time sitting in the car, he had a better opportunity to label the maneuvers accurately. Labeling data in offline causes some problems. First of all, sometimes slight maneuvers such as a lane change are not very obvious in the data. So looking at CAN bus data, you can't really with high confidence say if a maneuver is happening. So some people use onboard cameras and other kind of information to kind of compensate for that. But still, we believe that a human operator labeling the data in real time would be the most accurate way. So basically, we focused on 6 maneuvers that we were interested in for the purpose of our work, which are U-turn, right turn, lane change to the right lane, and lane change to the left lane, as well as left turn and hard brakes. And as you can see on the figure on the right, you see the distribution of this data, basically, which shows how this data is distributed over our data set. It's a almost balanced data set, which has most of which has basically an equal portion for each of these maneuvers. This data set is publicly available on GitHub. You can find the link on our paper. And again, feel free to reach out to me. The edition that we posted on GitHub currently is the first version, which is a limited data set. It includes, it's still relatively large. It includes about 500 maneuvers, which is pretty good. Actually, we'll show in our results that it's actually using a very simple classifier. You can actually look at these different maneuvers. But an extended version of this data set is also going to be posted on GitHub. If you're interested, please reach out to me. I might be able to give you more details. So looking at some examples of what kind of like information we are looking at the data set. Here we are looking at a right turn maneuver, and our feature space is larger. Here we only look at engine speed, accelerator pedal position, steering wheel angle, and vehicle speed. So engine speed is basically in RPM, and vehicle speed is in miles per hour, and the accelerator pedal position is just the percentage of the accelerator pedal that the driver is pushing. So here you can see basically when the steering kind of starts around 100, around the time step 100, you can see before that the engine speed is kind of going down and the vehicle is kind of slowing down. That's kind of what we do. We kind of slow down, bring down our speed, we make the right turn, and then start accelerating again. As you can see in both engine speed and accelerator pedal position, after the steering is kind of complete, that's what usually a human driver does, right? We start kind of accelerating again around 150. So this is just an example, and as you can see, probably you might say we don't really need these different kind of like features and dimensions to our data. We can only look at a steering wheel angle and classify the maneuvers based on a steering angle. That's correct, because some maneuvers by nature are more correlated with some specific feature space. For example, turning is obviously more correlated with the steering wheel angle, whereas hard brake is more correlated with vehicle speed, obviously. But what we emphasize on is this kind of rich feature set enables the classifying more accurately, because let's revisit what was our purpose of doing this work. We would like to have a labeled data set based on maneuvers, so we can train a classifier model in order to classify all other driving data. And basically we'll show that using a very simple classifier, a very naive classifier, we are able to actually train models that work pretty good in terms of classifying data. So that's actually the strength of this data set, that although it's not very large scale, the current version, as I said, only includes 500 maneuvers and more than 1,000 minutes of driving, recorded driving, but it's actually able to train a model very well for at least these 6 maneuvers. And let's explore some results, some samples. Here, as you can see on the figure on the left side, we have a right turn and left turn maneuvers, left turn in blue and right turn in red. And as you can see, the amplitude and basically the angle difference that we make in a left turn and right turn are very different. And we believe that's because of the design of our roads, because here we have left-hand side drive vehicles, and thus our right turns can be more sharp compared to left turns, in which we make a bigger circle. And as you can see, the steering angle is smoother compared to right turns. Although one might expect them to be pretty symmetric, this is something that we've seen in data that they're actually very asymmetric. And the figure on the right-hand side, we compare a U-turn and a left turn in terms of, again, a steering wheel. And although the patterns look similar, so if the data set wasn't labeled in real time, an annotator might look at these and kind of get confused between these two, because they look pretty similar. Their amplitudes are different, which makes it different between a U-turn, which has a very sharp steering angle, more than one turn. As you can see, it's more than 400 degrees as compared to the left turn. So as I said, we had our data basically collection campaign, and we manually labeled the data and parsed them to maneuvers. Then we trained a model with two very well-known and simple classifiers. And this was on purpose. We chose the simplest possible classifiers to show that our data is basically it's probabilistically significant in order to be able to train a model. So we use a support vector machine classifier, an SVM, as well as a random forest classifier, and trained two models and then tested them on some test set data. And our results, as you can see, on the left-hand side, we see the results of the SVM, and on the right-hand side, we see the results of the random forest. And as the confusion matrices show, they're pretty diagonal, which means that the classifier has learned a good amount of information from the data. And the same thing can be illustrated in terms of F1 score, precision, and recall. Again, on the right three figures, you are looking at the results for RF classifier. On the left-hand side, you're looking for the SVM, and we have shown the results for each of the basically maneuvers. As you can see, hard brake is a pretty obvious, I would say, maneuver, because you usually go straight, everything is fixed, your speed suddenly goes down, your RPM goes down, and you let go the accelerator pedal. And you can see the recall is pretty large on hard brake, actually. And the results show that actually our data set was able and was sufficient to train a model. This model can be used to annotate and classify the existing driving data sets, which can be a big contribution considering the fact that we already have a good amount of driving data which is not annotated, and the human annotation for these large data sets would require a lot of time and basically investment. So here, as a summary, we showed that our data set is publicly available. We showed that we were able to train two models, and the results kind of show that these two models work pretty well on the validation data. Thank you so much for your time. I hope you're staying safe, and please feel free to reach out to me and check out our lab's website. If you have any questions, reach out to me or my collaborators, and we would be happy to provide you with more information. Thank you.